In ring networks of non-locally coupled chaotic maps, we investigate the influence of additive Gaussian noise on spatio-temporal dynamics. The local dynamics of network nodes are governed by the logistic, Ricker, and Henon maps. By constructing 2D distributions of the probability of observing chimera states in terms of coupling strength and noise intensity, we uncover an optimum noise level that maximizes the likelihood of chimera states across a large number of realizations with randomly distributed initial conditions and noise sources. This phenomenon, referred to as chimera resonance, demonstrates a constructive role of noise, analogous to stochastic and coherence resonance. The probability distributions reveal that chimera states are most likely to emerge at an intermediate noise level, beyond which the noise intensity disrupts the chimera state. Our results provide insight into the interplay between noise, coupling strength, and local dynamics in shaping the spatio-temporal behavior of ring networks. The identification of an optimum noise level for chimera states has implications for the design and control of complex systems, where noise can be leveraged to induce desired patterns and behaviors. The study of noise effects on complex nonlinear systems has gained significant attention, particularly with the discovery of special spatio-temporal structures such as chimera states and solitary states. Chimera states represent partial synchronization patterns where coherent and incoherent dynamics coexist in networks of coupled nonlinear oscillators. Solitary states, characterized by a coherent part and isolated spikes, correspond to elements that behave differently from the coherent nodes. Noise sources can be introduced into complex systems and networks through additive or multiplicative noise, with varying characteristics and statistics. Previous research has shown that introducing noise can induce novel spatio-temporal structures, such as coherence resonance chimera in neural networks and solitary state chimera in networks of chaotic oscillators. This study systematically examines the impact of additive Gaussian noise on the dynamics and chimera observation in networks of non-locally coupled discrete time systems. Using the logistic map, Henon map, and Ricker map as individual elements, the researchers construct 2D diagrams of typical dynamical regimes observed in noise-free networks. They calculate the probability of observing chimera states when the noise intensity and coupling strength are varied. The numerical results reveal that the chimera existence demonstrates a resonance-like dependence on the noise intensity and coupling strength, with an optimum noise level at which the interval of the coupling strength within which chimera states can be observed is maximized. This phenomenon is reminiscent of the constructive influence of noise known from coherence resonance. However, the probability level of chimera observation in noisy networks of coupled oscillators remains unclear, depending on the local dynamics of individual nodes and the variation of coupling parameters. In networks of chaotic maps, chimera states have garnered significant attention. This research delves into the study of chimera states in a ring network of non-locally coupled discrete time systems, where additive noise is incorporated into the system of equations. The network comprises individual elements, each represented by a discrete time system, specifically the logistic map, the modified Ricker map, and the Henon map. These systems are characterized by chaotic dynamics and multistability. The logistic map exhibits a period-doubling bifurcation cascade, ultimately leading to chaos. Similarly, the modified Ricker map displays a comparable behavior, albeit within a distinct parameter regime. Notably, the Henon map, when reduced to the logistic map at specific parameter values, also exhibits chaotic behavior. By investigating these systems within the network, this study aims to elucidate their interactions and the influence of noise on their behavior, particularly in the context of chimera states. The non-local coupling scheme employed in this network enables the exploration of complex interactions between the individual elements. The inclusion of additive noise allows for the examination of its impact on the emergence and stability of chimera states. By understanding the interplay between these chaotic systems and noise, this research provides insights into the mechanisms underlying chimera states in networks of discrete time systems. The authors investigate the emergence of chimera states in networks of chaotic maps, focusing on the transition from complete chaotic synchronization to spatio-temporal chaos as the coupling strength decreases. They study the spatio-temporal dynamics of the network for multiple realizations of randomly distributed initial states and noise realizations. To quantify changes, they use instantaneous spatial distributions of dynamical variables and spatio-temporal diagrams. The cross-correlation coefficient between network elements indicates the degree of correlation between nodes, diagnosing network dynamics and identifying spatio-temporal structures. Results show that additive noise can induce chimera states within a wide range of non-local coupling strengths, with a constructive role of noise akin to stochastic and coherence resonance, referred to as chimera resonance. The authors consider a network of non-locally coupled logistic maps, varying the local dynamics parameter and the coupling strength. They observe 4 distinct regions in the parameter plane, corresponding to coherent, incoherent, and chimera states, as well as snapshots with profile discontinuities. Exemplary snapshots, spatial distributions of the cross-correlation coefficient, and spacetime diagrams are presented for each region. The alpha L range can be divided into 2 subranges, each corresponding to a different transition from incoherence to coherence as the coupling strength increases, with or without the appearance of chimera states and profiles with discontinuities. In networks of chaotic maps, the phenomenon of chimera resonance is explored, with a focus on the coherence region for alpha L within 3.68, 3.71. 2 distinct transition pathways to coherence are identified, involving incoherence, chimera states, and snapshots with profile discontinuities. The study examines the effect of additive Gaussian noise on the probability of observing chimera states, presenting 2 parameter diagrams of oscillation period distributions and corresponding temporal dynamics. Within the coherence region, the network exhibits either regular or irregular dynamics, with period doubling bifurcations emerging as alpha L increases. The introduction of Gaussian noise significantly affects the observation of chimera states, extending the interval with high probability and inducing the appearance of chimera states. These findings provide insights into the complex interplay between noise, chaos, and coherence in networks, highlighting the importance of considering the impact of noise on chimera resonance. The phenomenon of chimera resonance in networks of chaotic maps is explored, focusing on how the probability of observing chimera states changes with varying noise intensity and coupling parameters. It is observed that noise-induced chimera states are more stable towards additive noise in the strong coupling range. The region of non-zero probability expands with both coupling strength and noise intensity as the local dynamics parameter increases. This highlights the novel idea of chimera resonance, where additive noise plays a constructive role in the observation of chimera states, shedding light on the dynamics of complex networks. In networks of chaotic maps, chimera resonance is a phenomenon where distinct regions exhibit synchronized and desynchronized behavior. This study investigates how additive noise influences the emergence and stability of chimeras in a logistic map network with non-local coupling. The authors demonstrate that introducing additive noise significantly enhances the probability of observing chimeras, even when they are absent in the noise-free scenario. A 2-dimensional diagram illustrates the probability distribution of chimera states as a function of coupling strength and noise intensity. This diagram reveals distinct regions where chimeras are likely to occur, with the probability of their observation increasing with higher noise intensities. For weak coupling, there is a finite range of noise intensities where the probability of chimera observation is almost constant. In contrast, strong coupling leads to a monotonic increase in probability, reaching a maximum value of approximately 1 over a wide range of noise intensities. However, beyond a certain threshold, the chimeras are destroyed, and the probability drops to 0. The authors also examine the effect of varying the coupling range R on the maximum probability of chimera observation. They find that the maximum probability increases with increasing noise intensity, but only up to a certain point, after which it decreases and eventually drops to 0 as the chimeras are destroyed. The corresponding coupling strength for the maximum probability also changes non-monotonically with noise intensity, exhibiting a dip around D approximately equals 0.006. This study highlights the crucial role of additive noise in enhancing the emergence of chimeras in networks of chaotic maps, and demonstrates how the interplay between noise intensity and coupling strength significantly impacts the probability of observing these states. Investigating chimera resonance in networks of chaotic maps, the authors focus on the logistic map network and the network of non-locally coupled Henon maps. The probability of observing chimera states in the logistic map network is examined as a function of coupling strength sigma and noise intensity d, as depicted in figures 6 and 7. The results reveal that the probability of chimera observation increases with sigma, reaching a maximum value before decreasing. This maximum probability is observed at a specific value of sigma, dependent on the noise intensity d. Furthermore, the width of the sigma interval at the mean probability level and at the level of 0.95 of the maximum probability exhibits a resonant-like form, peaking at an optimum noise level d. The authors also explore the impact of the coupling range R on chimera resonance, finding that the maximum probability of observing chimeras increases with R. Conversely, the width of the sigma interval decreases as R decreases, with the maximum width observed at R equals 340 and the minimum at R equals 280. Shifting their attention to the network of non-locally coupled Henon maps, the authors analyze the effect of additive noise on the probability of observing chimera states. This comprehensive examination of chimera resonance in chaotic map networks provides valuable insights into the complex interplay between coupling strength, noise intensity, and coupling range. The authors investigate chimera resonance in networks of chaotic maps, focusing on the dynamics of non-locally coupled Henon maps. They construct 2D diagrams of dynamical regimes and corresponding temporal behavior in the alpha h, sigma parameter plane for two different realizations of initial conditions. The diagrams reveal four typical dynamical regimes: coherence, chimera states, incoherence, and snapshots with profiled discontinuities. For alpha h between 1.0 and 1.15, the network exhibits coherent dynamics, characterized by periodic oscillations with t equals 4 and t equals 8 due to period doubling. A transition from incoherence to coherence occurs through the existence of chimera states when alpha h is between 1.15 and 1.6, with two distinct routes identified depending on the presence or absence of a coherent window. The Henon map network exhibits an earlier transition to coherent dynamics with respect to sigma than for larger values of alpha h. The authors also investigate the influence of external noise on the probability of observing chimera states, plotting distribution diagrams for the probability p of observing chimera states in the sigma d parameter plane for different values of alpha h. These diagrams show that the probability of chimera observation is affected by the value of alpha h, with one or two regions of high probability emerging depending on the strength of the coupling and noise intensity. The dynamics of networks of chaotic maps, particularly chimera resonance, are discussed in this section. It begins by examining the probability distributions of chimera observation in networks of non-locally coupled Henon maps, emphasizing the impact of chimera resonance. These distributions are more extensive in size for larger values of the parameter alpha h, with a shift towards stronger coupling and a larger noise intensity range for chimera existence. The analysis then moves on to a network of non-locally coupled modified Ricker maps, demonstrating that it can exhibit both chimeras and solitary states as the local dynamics parameter alpha r is varied. The results are presented in 2D diagrams of spatio-temporal regimes and temporal dynamics distributions in the alpha r, sigma parameter plane. Finally, the section concludes by discussing the regimes of solitary states in the Ricker map network, including their transition to chimera states with increasing coupling strength. This research provides valuable insights into the complex behavior of chaotic map networks and their potential applications in various fields. This section of the research paper delves into the impact of additive noise on the probability of observing chimera states in a network of modified Ricker maps. The authors present their findings through 2D distribution diagrams for the probability p and the sigma d parameter plane. In the absence of noise, d equals 0, chimera states are not observed for alpha r less than 17.2. However, the introduction of additive noise, even at low intensities, leads to the emergence of chimera states with a high probability in the range of strong coupling. This is evident from the distribution in Figure 12a, for alpha r equals 17.5, which shows a single and wide region with respect to both sigma and d within which p is essentially equal to 1. For larger values of alpha r is greater than or equal to 18.5, the region with a high probability of chimera observation is split into two parts separated by a channel within which p approximately equals 0.5, figures 12, b, c. This channel narrows and eventually degenerates into a small island, with a lower probability value as alpha r increases, figure 12, d. The presented probability distributions verify the manifestation of chimera resonance with respect to both the sigma interval and the Drange corresponding to a high probability of chimera observation. Notably, unlike the logistic map and Henon map networks, chimera states exist even for sufficiently strong noise up to d approximately equals 0.15 in the Ricker map network. Furthermore, the existence of solitary states within a narrow region in the alpha r, sigma parameter plane for strong coupling and large values of alpha r can affect the distributions of the probability of observing chimera states already at a low noise intensity. This is illustrated in figures 12, e, f, which show that at low noise levels and sufficiently strong coupling, the region with a high probability of chimera existence is cut by a triangular region in which incoherent dynamics takes place. The authors delve into the impact of additive noise on the dynamics of networks of chaotic maps, focusing on the modified Ricker map network. They reveal that the presence of noise can either induce or suppress chimera states, depending on the noise intensity and coupling strength. For large values of the coupling strength alpha r, the noise intensity shifts the control parameters to a narrow region where solitary states exist, leading to incoherence and a gap in the distribution diagrams for the probability of chimera observation. In the first case, with a low noise intensity, phase chimeras emerge with narrow incoherent clusters. As the noise intensity increases, it leads to the zero probability region and incoherent dynamics. Further increasing the noise intensity returns the system to the region with high probability of chimera observation. In the second case, where solitary states exist in the noise-free network, a gradual increase in the noise intensity initially has little effect, then leads to the disappearance of solitary nodes and the emergence of chimera states, followed by a return to incoherent dynamics and finally to the existence of chimera states at high noise levels. The authors conclude that the presence of additive noise significantly affects the probability of observing chimera states in networks of chaotic maps. The noise intensity can either induce or suppress chimera states depending on the coupling strength and local dynamics. Chimera resonance in networks of chaotic maps is a phenomenon where external noise plays a constructive role in enhancing the stability and formation of spatio-temporal structures known as chimeras. These chimeras are characterized by the coexistence of coherence and incoherence among non-locally coupled oscillators. By varying the coupling strength, non-local coupling range, and noise intensity, the probability of observing chimeras in three different networks logistic map, Henon map, and Ricker map networks is influenced. A specific interval of the coupling strength, dependent on the local dynamics parameter of individual nodes, is identified where the probability of chimera existence is high or even maximum. The presence of solitary states in a network, as seen in the modified Ricker map network, significantly affects the shape of the probability distribution of observing chimeras. Moreover, an optimal non-vanishing noise level is found, at which the sigma interval corresponding to a high or even maximum probability of chimera observation is the largest. A finite range of the noise intensity d is identified, within which chimera states are observed with a high or even maximum probability. This Drange is the widest at a certain, resonant, value of the coupling strength sigma. The findings of this study contribute to the understanding of the interplay between dynamics, structure, noise, and delay in networks, highlighting the potential for controlling the formation and stability of chimeras through external noise. The research is supported by previous studies on the impact of noise on the amplitude chimera lifetime in an ensemble of non-locally coupled chaotic maps. In complex networks, chimera states have garnered significant attention due to their unique synchronization and desynchronization patterns, characterized by the coexistence of coherent and incoherent behavior in different parts of the network. Stochastic resonance, a phenomenon where additive noise enhances the coherence of a system's response to a weak periodic signal, has been applied to bistable systems, leading to the emergence of solitary states in adaptive non-local oscillator networks. Delayed feedback plays a crucial role in controlling chimera states, and multiplexing noise can induce synchronization in multilayer networks. The transition from spatial coherence to incoherence in ensembles of non-locally coupled chaotic oscillators with non-hyperbolic and hyperbolic attractors has been investigated, revealing that hyperbolicity can impede the emergence of chimera states. The interplay between fractal topology and delay in complex networks significantly influences the formation of chimera states. Experimental observations of chimera states have been achieved in coupled map lattices and populations of coupled chemical oscillators, while virtual chimera states have been observed in delayed feedback systems. These findings highlight the relevance of chimera states in various physical and biological systems. Understanding the mechanisms underlying chimera states is essential for controlling and manipulating them, with potential applications in real-world systems, such as neural networks, to enhance or disrupt synchronization patterns as needed. The complex interplay between noise, delayed feedback, and network topology is crucial in the emergence and control of chimera states, emphasizing the need for further research into these factors to harness the potential of chimera states in complex networks. Chimera states in networks of chaotic maps exhibit coexisting synchronous and incoherent domains, a phenomenon characterized by intriguing spatial patterns and complex dynamics. These states can be categorized into distinct types, including spatially organized dynamical states, which feature robust and stable patterns, and imperfect chimera states, which display fragile and volatile structures. Additionally, transient scaling of chimera states has been observed, wherein the system exhibits a power law decay of the synchronization error. Experimental investigations have been conducted using coupled electronic oscillators, revealing the properties of chimera states in these systems. Furthermore, the dynamics of Kuramoto oscillators with time-delayed couplings have been studied, shedding light on the mechanism of solitary state appearance in ensembles of non-locally coupled lossy maps. These solitary states, characterized by a single oscillator deviating from the synchronized group, have been found to respond sensitively to noise-modulated parameters in non-locally coupled networks of lossy maps. The study of chimera states in these systems has significant implications for our understanding of complex network dynamics, synchronization, and pattern formation. The findings have the potential to inform the development of novel control strategies and synchronization techniques in a wide range of applications, from neuroscience to engineering.